Good morning, everybody. We are going to start with soils and with spectroscopy techniques. Perhaps it's a bit hard for the first talk in the morning, but we'll see. I hope you enjoy it and you understand it. It's a bit difficult, but I'm going to explain it. It's difficult for me, mainly. So I will try to do my best and explain it as best as I can. First of all, starting with soils, we need to understand that we have organic forest horizons and a mineral soil. The organic forest horizons have a key role in nutrient cycling, also in maintenance of soil fertility, and they have a high contribution on carbon sequestration in forest soils. The organic soils, as you can see, are this part of the soil where the part that is closer to the vegetation, okay? So litter decomposition in soils releases essential nutrients as nitrogen or phosphorus into the soil, and evaluating or assessing litter composition is key to measure nutrient availability, also cycling rates, facilitates sustainable management to improve carbon sequestration, and also help us to evaluate the health and resilience of the forests. Traditional methods for determining the total organic carbon and the total nitrogen, that are two properties in the soil that are very important in the soil and in litter, of course, provide high accuracy and precision. But these methods are costly, are time-consuming, and sometimes are associated to environmental impacts. So looking for or developing new methods or new techniques that are reliable, rapid, and cost-effective is very, very important. It's why we from years ago, infrared spectroscopic techniques are using for these purposes. These techniques are widely used to estimate physical and chemical properties in soil samples, but when we use this type of techniques in litter samples, so in organic soils, the success of the techniques are not so good. The mid-infrared spectroscopy, the MIR, allows the identification of functional groups, for example, carboxyls or esters or others, in solid and liquid samples in the region of the MIR, which is this region here that you can see here, from 4,000 to 400 centimeters wave number. Okay, in the electromagnetic spectrum, which is this one. So then we have the FTIR. The FTIR is a technique that measured in the MIR region, okay, in the region that I already said, and is an analytical tool that allows us to identify organic and inorganic compounds in the soil, on the litter fall, whatever. And then we have another technique, which is the ATR, the attenuated total reflectance, that also is used in the MIR region and allows obtaining infrared spectra of samples without preparation. We just need to have the samples milled, and that's it. This technique is rapid, cost-effective, environmental friendly, non-destructive, and reproducible. And it's very common to study to do this type of works in soils. We can use this technique for two purposes: characterization and quantification. And for quantification, what we need is to have calibration processes. For this calibration process, we need two types of variables: the independent variable, which are the absorbance measures at different wave numbers, and the dependent numbers, which are the parameters or the properties of the soil or the litter fall that we want to predict. In this case, we're going to predict the total organic carbon and the total nitrogen. The resulting mathematical equation from this process of calibration is the quantitative calibration model that we are going to use to determine soil properties concentration from other samples, different samples, and that we can use it in the future to predict these properties. So our objective is to evaluate the effectiveness of this technique, the ATR-FTIR technique, in the MIR region to predict in the future two properties of forest soil organic layers, which are the total organic carbon and the total nitrogen. We sampled more than 240 forest soil samples, but not forest soils, organic soils, and I missed the word there, organic soils, from an European forest plot network that you can see in the map. We sample organic layers from Pinus sylvestris, Quercus, and Fagus sylvatica in monospecific and mixed forest stands. And we also differentiated between the different types of litter layers, which are the undecomposed layer, the fresh litter, the intermediate decomposed layer, and the humified litter. So here you can you can see a spectra of the ATR-FTIR technique. You can see the spectra that we get are something like this. And remember that we are recording in the MIR region, okay? And then what we evaluate is the different peaks of the spectra, which are related to different functional groups. So with this, we develop models with partial least square regression, which is the usual method, a statistical method that is used in this type of works. And also we did generalized mixed models, including forest stands type, species, and litter layer type. These three things in both type of methodologies. What we want to do? To develop equations for total organic carbon and total nitrogen concentration predictions. So we want to predict in the future with new samples these two properties. This is one of the spectra that we get from our results. This is for fresh litter, so the undecomposed layer from all the three species that you can see here. And as we can see, the spectra is more or less the same for all the three species, but we have 3 points where the fresh litter of these three species differ. These 3 points are here in the circles. In this wave number, this signal are correlated or related with ester and carboxylic acids. In this other part, the signals are related to catechins and waxes, and in this other part, the signals are correlated with polysaccharides. As I said before, what we do with the spectra is to each peak of the spectra is going to be related with different functional groups. This is very well known because due to other works in the past, okay? So, what we found, predictions of the total organic carbon and total nitrogen concentration in the litter samples was better with the generalized mixed model than with the PLS. This could be because we think that usually in these works people use PLS because when this type of works started, the other statistical techniques that are more robust or can use other type of data were not very common. So the PLS was the statistical technique that was more useful for this type of data. Now, with the generalized mixed model, we think that these type of models are better for the complexity of this type of data that we get with the spectrum. Here you can see in the table that, well, these three parameters are important for the models to know if the model is, has a good prediction performance or not. These two should be near 1, and this is better to be lower as possible. What we see that in soil, when people work with soil, the models are much better. For example, this parameter is almost 1, which is great. But our results are in line with other works that work with litter samples, and moreover, our results with the generalized mixed model are better. So the model predicts better the concentration of these two parameters than in other works. For this, I would say that the use of the generalized mixed model could be an alternative to the traditional method, which is the PLS, for this type of works and studies. And we need to work more in this because we are starting with this topic, and I hope next year I can tell you more things about this. And that's it. Thank you very much.